for that to get working. Okay. So we left off last night trying to figure out the correct math for our voxels. And we got a little bit of weirdness because we're going to take a 256 by 256 section of memory, and we're going to pretend it's a 512 by 512 section of memory by kind of like partitioning out the R, G, B, and A channels, right? So we're going to like split out the R, G, B, and A, and we're going to pretend that R is the first quadrant of this 512 by 512, G is the second quadrant, B the third, and A is the fourth, right? And in order to know which one of these quadrants we're in, we're going to use CSC, which is going to stand for cross-section color, I believe. And well, actually, we can look that up right now. So in our documentation, we've kind of meticulously said what like all of our variables are, and we see that CSC is for cross-section color. So we're going to try this style of keeping really meticulous documentation in one file, and then we can try to keep the code just like a little bit cleaner because all of the code doesn't have as much comments. Now, obviously, we still ended up writing comments because we ended up getting kind of lost in our logic, and we weren't sure about how we were doing all of this. So let's open up Shader Toy. So let's open up, actually we already have a Torch browser over here. Let's open up a new tab. Let's put one over here. And do we have like a tinyurl.com/sdf 019 demo? Do we have that yet? If we don't have that, we're going to set that up right now. Yeah, we don't have that, so let's go to www.shadertoy.com, and let's set up that URL right now, since that's kind of one of the ones we want to use right now, and I think that's the most valuable. Alright, so let's look at some of our unlisted shaders here. So this SDF19. Okay. So we want to just take this shader that right now. We want to take this shader right now, and we want to make sure that that it's set up properly really quick. And okay, we got our buffer, we got our image. So I'm pretty sure this is set up correctly. It's working how I would expect it to. So we just want to take this code and we want to get a tiny URL for that. So tinyurl.com. And actually, before we do that, this is the demo URL. So let's go into the main documentation code here, and let's put that in our list of stuff here. So we can see that we have the Shader Toy URL that should be going right here. We can paste that right there, shadertoy.com/view, whatever, and we can double check, make absolutely sure that that is the correct URL. Food. Need food. So that looks good. Let's just take that. We'll go over here and we'll go enter this long URL. We're going to call it SDF-019-demo because this is the demo code, the actual code that's working. So make that into a tiny URL and SDF-019 demo. And then let's absolutely make sure that works. So www.tinyurl.com/SDF-019 demo. Okay, so I need food, but I don't have enough followers to recommend me what to eat, so I guess I'm gonna starve. But I don't need anyone's pity. I'll make it on my own. Also, mixing nutmeg with cocoa without sugar was a bad idea. It tastes horrible. But, you know, I can't have coffee right now, so I'm just trying my best. Okay. So this works. We got the little demo stuff. Let's look at the code here and try to make sure that the code is correct. Why do you keep putting weird shit in your drinks? I see. You think you have a right to judge? Okay, so let's make sure that all of this math is correct. So for this VOB XYZ, we just want that to be the voxel X, the voxel Y, and the voxel Z, and we want to be able to extract a voxel value in the range of 0 to 255. So the first thing I want to check here is, do we even have VX, VY, VZ in here? And it looks like we do not. So we're gonna throw it in maybe over. I guess we should throw it in kind of like where it makes sense for it to be. So over here we'll do VX, and now sometimes people might use like VX for velocity X, velocity Y, velocity Z. Hopefully we never have that problem because we're just doing rendering code, and rendering code doesn't have velocity in it. Well, that's a lie. I mean, Doom's 2016 engine has a thing called a velocity map to help calculate motion blur, but we're not that badass, so I doubt we're going to have a velocity variable. So we can use this for voxel X, voxel Y, voxel Z. So let's do that. So VX, voxel, voxel X, and that's so an important thing is that we're going to abstract voxels into. We're not thinking of voxels as just three-dimensional pixels. We're thinking of them as three-dimensional tiles, but we're also thinking that within a tile, you can go into that tile and go march into a pixel, and within a pixel, you can subdivide that pixel, and then that sub-pixel you can also subdivide, and we only really have words for the voxel and then the pixel. So rather than calling, eventually, when we get down to certain levels, it's better, instead of to come up with random-ass names, to just be like, it's a Von 0. So a voxel is a Von 0, and then a pixel within a voxel is a Von 1, etc. So VX, VY is going to be voxel Y, and we'll do Von 0.y, Von 0, 0, and this is just the different ways that I could imagine writing it. So VZ is going to be voxel Z, and Von 0.z, Von 0, 0, 0.y. And that's kind of confusing to have the slash, because that's kind of thought of as division. So we might want to think about, well, how are we going to make that clear that it's not division? I mean, we could use this, but, right, that's also a bitwise OR. So how are we going to make it certain that it is a slash or an alias, right? So we could just do 2 slashes to say it's this or that. We could do that, so there's a little bar and a slash to be like slash or this. I don't know. We could do that for now. That looks a little verbose, but I just want to make sure that we don't think of this as an equation. Also, since we're kind of doing this, it's important to be TX, tile X, only for 2D data. So this time, last time I wanted to keep the tile map analogy and just say, oh, well, voxels are just three-dimensional tiles, so let's do tile X, tile Y, and tile Z. This time I think I want to not do that, and we're going to say that if we have a tile value, tiles are going to always be two-dimensional. So TZ, no such thing. Tiles are now. Okay. So basically, tiles are only 2D. So if we see TX, TY, there should never be a TZ. So just a little note. It's also important to know what we don't use as well. Why do you keep putting weird shit in your drinks? Because, I can't have sugar. So okay. So we have this TX, TY, TZ. That's good enough there. And let's look at our diagram and check our math and see if these make sense. And also, wait, let's look at our function names. We got get tib, get tile byte, get voxel byte, right? And tile byte is tiles are 2D only. Voxels are so we're gonna keep this convention now. I don't really like that, so let's do we have these different sections. Let's do a I like the I like trying to keep everything to one line here and keep a nice little index. So disambiguation. I don't know how to spell that. Let's look it up. Showing results for disambiguation. Oh boy. So TUCMD. Okay, so if we type, let's put that in our shortcuts to try to make sure that we never spell it wrong again. So disambiguation. Well, of course that's not correct. What the hell? Okay, disambiguation, right? So, in our disambiguation section, we will we'll clarify get tib versus but really that's not what we care about. Yeah, I don't know. So over here, let's do tib, is going to be tile byte. And then Bob is going to be voxel byte. And tiles are 2D. And then voxels are 3D. I don't really know where to put that. As long as we kind of know what we're doing, that'll be fine. Okay. I think that's good. Let's go back to our diagram and kind of figure this out. Because we, at 3:30, we got to get out of here. So... let's look at this first. So if we have an X, Y, and Z, we're thinking of X and Y as X and Y locates is the two-dimensional aspect, right? So when we use X and Y, we just think of it as a location on a two-dimensional cross-section. And for Z, we just think of Z as which cross-section of the tile map we're on. So let's try to work through this and see how we're doing this. So cross-section color, we're taking the VZ and we're dividing it by 16. And why is that? So, right, Z tells us what cross-section we're in. And in this diagram here, in our layout here, right, we're going to think of the cross-sections stacked next to each other on this 512 by 512 grid. But another analogy for how these cross-sections are stored is that they're in like a little skyscraper. And the skyscraper is actually upside down, right? So this is the first floor, second floor, third floor, and fourth floor down here. And, right, 16 floors, 16 floors, and 16 floors, and 16 floors, right? And so we could say that so let's take this RGBA for a second, and let's kind of make some more drawings here. Let's actually take this. We're gonna take it. We're gonna put it over here just so I can see it a little bit better. And okay, so with R, we have R, G, B, and A, right? So let's take this and just duplicate it a few times. So this is CSC equals 0. This is CSC equals 1. Oh, what the hell now? And then over here is CSC equals 2. And then over here is CSC equals 3, okay? And, right, and we have the different tile values, so we could actually do the we could actually make a note of what the VZ value is, right? So so this is VZ. We could do 0. So VZ is greater than or equal to 0, but less than or equal to, we could do 15. Right? And then we could copy this. Right? Because remember, we're always going to think of voxels as kind of like abstracting a tile map into 3 dimensions, and the way we'll do that is we'll just stack multiple 2-dimensional cross sections onto each other, right? So for this, let's just copy it all first, and we have 16, and we have 32. And this should be 48. And 16 to 31. 32 to 47. And then this is to 64. So even though we're not going to use the 64th, we're going to think of the voxel map as, when we're rendering, we're going to just use the, we're not going to use the last 64th cell. We're going to just use 0 to 62 rather than 0 to 63. We're not going to use that last one. And this is actually wrong because this is supposed to be 63. So 63, right? And so we can think of, so the cross-section color kind of tells us what height we're in the skyscraper. And really, the thing is that with our analogy, with how we organize the data, it's backwards. So instead of using a skyscraper analogy, I think it makes more sense to think of it as like a little missile silo, right? So let's take all this and let's put it backwards like this. Okay. And we're just gonna call this a, you know, to make it easy to kind of like have an easy analogy for this, we're just gonna say tip of missile silo. Higher values mean we are deeper into data, into the data. Alright, so we're gonna think of it as like a little missile silo here, right? And over here, these are some clouds. Just use your imagination. Got some clouds, and here's the ground, right? And this is just the tip of our missile silo. So if we look down here, we have R, G, B, and A. So now, yeah, using kind of like a missile silo analogy, I think makes a little bit more sense than a skyscraper analogy for getting this math correct. So now that we know that the voxel X kind of the voxel Z kind of tells us where we are in this cross section, and we just have to divide by 16 to figure out which one of these cross sections we're in, right? So going over here, we see that indeed we're dividing by 16, and then we truncate the result, and that figures out which cross section we're in. Then when we want the first floor of the so the first floor of this is the first floor of a certain color. And even though we're going to think of a missile silo analogy, this still would work, right? Because because you're walking from the top and you're walking downwards to get deeper and deeper. So this is going to be the first colored floor you hit, and it's the cross-section color multiplied by 16, right? And let's make sure that CSF is in our documentation, right? So let's go back to our documentation tab and go CSF. Make sure that is in the correct place. So CSF, cross-section, first floor of given color. That works. And CSL is the cross-section, I believe, layer. Yeah, so we take the first floor of a given color. And, oh, this is local is what that is, right? Yeah, because we're going to take VZ, and we're going to subtract the first, like this value, this F value is a global value. We're going to take VZ and subtract out that global value to get this local floor index, right? So the first floor of any color is 0, right, when we're looking at the local index. And once again, we can go back here and look at CSL. And also we look cross-section index, we use CSL. In CSG, we're going to say to use CSF, right? So we know that CSF here is like a global floor location, and CSL is kind of the local floor location. So once we have that floor location, we want to get the X and Y, and the way we're going to do that is looks like we're doing some tile map math with 4 and 4. So we're going to take those 16 floors and think of it as a 4x4 grid. So let's look at where we're doing that. So let's say we're in the green section. Well, within the green section, there are 16 floors. Like this range includes 16 different floors, right? And when we're looking at this green cross section, we take this we want to take all that data and put it into a 256 by 256 kind of area. And then we can divide all the values into kind of this grid, and then we can use the X and Y on this data set here to figure out what the X and Y, we're going to use X and Y on here to figure out, so we know we're in this set of floors, and we're going to take this set of floors and we're going to transform it into, instead of a set of layers, we're going to take this set of layers, and so this is a set of layers here, and we're going to partition them out like this in two-dimensional space. So this is a two-dimensional view of all those different floors. And why are we doing it that way? Why not just like a big linear strip? Why not just a big linear strip? Yeah, this is a little bit weird of a way to do it. I kind of see why I'm doing it this way. I think this might be kind of like over-engineered, because it's kind of confusing me that we have kind of like, oh, tile maps are these different layers, but we store the layers in this weird-ass way. But this is the way we've kind of designed it, so let's just, oh, you know why we're doing it this way? We're doing it this way because we need to make absolutely sure the memory is compatible with the 512 by 512 block with those dimensions, with those actual physical pixel coordinates, and that's why we're kind of abstracting the math this way. So once we get like the floor layout here, right, then we can know which one of these cells we're in. Which one of these cells we're in is based on the local value, right? So the CSL value will identify which one of these cross sections we're in, right? And we already have the CSL, and now basically what we're doing is we're doing the index to XY formula, right? So we already know which one of these cells we're in, right? Because we got the cell from this kind of calculation over here, and now we just want to figure out what that X and Y is, right? So, you know, index to XY formula will give us the X and Y of those cross sections. And then the cross section origin, right, is we got to take those values and then we got to multiply them by 64 to get these upper corners of these, right? So we have these as cells, but if we want to look at the actual pixels inside of them and figure out where the origin is, right, we got to take this cell value here and multiply by 64 will be over here. 1 multiplied by 64 will be over here. 2 multiplied by 64 will be over here. So these are the cell indices, and then to get the origin of the pixel index, that's how we're going to do that. Okay. So then after we have the origins, and let's make sure we have the origins. Do we have the COX, COY? Are those in there? Yep, they're in there. Pixel X, pixel Y, we're going to take those origins, and we're just going to add VX and VY. So VX and VY are always local to the cross section, right? So remember that we're abstracting our map data as VX and VY are just X and Y that exist on a 2D tile map, and VX and VY are coordinates on a 2D tile map, and VZ is a different cross section, right? So we just have a whole bunch of 2D tile maps stacked on top of each other. So that abstraction is still there. And then once we have the PX and PY, we can do a Texel fetch. Now, my question here is, the Texel fetch needs to be with a 256 by 256. Is this correct? Is that going to be 256 by 256, or have we screwed that up? So if we look at the diagram, let's look at our diagram again. And this right here is 64, 64, right? 64, 64 is 128. 128 and 128 is 256. For cell, so this is for cell, but it's also 256. So right, so when we're looking at the units here, it's 4 cells, but it is 256 pixel, right? So we have these different units here, and if we want to, let's just make absolutely sure, you know, if we have 64 times 4, we do get 256, right? So that means that our Texel fetch, we'll make sure that PX, so PX equals 0 to 255, right? Or 256 minus 1 if you want to think of it like that. And then, you know, PY equals 0 to 256 minus 1 as well. So a thought here is that, you know, we want to avoid being really verbose with our comments, but we also want to maximize the space as well. So there's unused space here, so let's take advantage of that and just write these comments here, right? And so we know that this Texel fetch is going to be somewhere between 0 and 256 minus 1. And I like that. Let's check our math, make sure that everything is correct. The byte, so I don't even know if this is allowable, but right, we're going to take the this color 4D, and we're going to take the RGB or A channel, and then we're going to multiply by 255.0, and then cast to U32 to get the byte value. Now, I don't know if we can actually look it up like this with this index accessor, so I kind of left this commented out code right here in case that is not the case. So, further down, let's look at this abstraction. So when we pass around the voxel values, we're going to try to use a voxel index that's not meant for a 256 by 256 chunk of memory. We're going to try to think of the voxel index as something that locates a voxel on a 512 by a 512. So we got to figure out how we get back to the original Vx, Vy, Vz using this 512. And it's a little bit more confusing than I would have had liked it to be. But really, we want to make sure that our analogies are kind of like compatible in the way that we've done this to make this 512 by 512. We gotta kind of keep this, right? So, even though it might make more sense for, well, actually, no. So, is that sensible? Yeah, so we want to just make sure that the way we're packing it into the 512 by 512 is just compatible with the way we've been doing it with the 256 by 256. And I could be wrong here with the way I'm thinking of this. Let's see, what's today? Today is the 3rd. I need to check my schedule here. So the 3rd, 6:30 p.m. So I still have some time here. So even though we want to think of everything as, tile maps that are kind of like layered on top of each other, so when we actually end up using a 512 by 512 section of memory, we will have, once we get the final coordinate, rather than having to use just the R, just the G, just the B, or just the A for the tile value, we'll be able to use R, G, B, and A. And so we'll kind of have, we'll have kind of like this way where once we're using a actual 512 by 512 texture, we'll kind of quadruple our possible values, and we could use that to have 4 overlapped voxel maps, possibly. We could say that one voxel map is like geometry, and the other one is lighting, and then another one is, say, enemies, and then another one is who knows what else, right? And we could have that all overlaid, right? Maybe, you know, we could have lighting, enemies, and particle-based effects, like maybe like fire can like overlay over certain voxels, right? And so we could get like all that kind of stuff for free once we move this over to like some C code. But that's a lot of extra work and stuff that we don't want to think about, and by constraining ourselves in this way to where we physically can't do that because we don't have that extra space yet when we're doing it in shader toy, that kind of makes it kind of nice. So yeah, I'm just thinking through this, and so yeah, this 512 section, yeah, so we're gonna pretend that we actually have a 512 by 512, right? So this index is going to pretend that we have a 512 by 512, and basically we want to use that 512 by 512 index type value to correctly traverse this data structure here, right? And correctly, and I don't know if this is going to be compatible or not. I almost want to start writing some JavaScript just to check my math here, because this is kind of like this is going to be hard to debug in the shader code, and I just kind of feel like there could be some type of fundamental assumption that I'm getting wrong here, and that could create problems for me. So we take the px 512 and py 512. So it's the xy coordinate when we're thinking that the that the index maps over just that this is like a linear index into a 512 by 512 bit map, right? So we're going to do like the index to xy math on that, and we'll divide 512, this vi 512 by 512, and we'll truncate it, and that'll give us the number of full y's, and then we'll do the y times 512, and this should be a U32 512. So then we'll multiply this, subtract from the base value, and this will give us the remainder. It'll give us a px value. So now we have this xy value on a conceptual 512 by 512 bitmap, and then we want to figure out what colored floors we're on. So these quadrants here, 512, 512, divide by 256, divide by 256, and truncate, and that will give us which one of these sectors we're in, right? The R, G, or the B, or the A, right? And then after we do that, we can do, now we have to convert it to an actual 256 by 256 X or Y value. And the way we'll do that is we'll take those quadrant values, and the quadrant value should either be a 0 or a 1, and we'll multiply that by 256. We'll minus from the base values here, and then we'll get a local px py value. That px py value, we can then do some grid collision with 64, right? So with so now we're kind of like, let's say we're inside of G. Well, Inside of G, we got to do some grid collision with 64 by 64 cells to figure out which cell index we're in here, right? So we divide by 64 because each one of those cells is 64, and then we do integer and trunc to get an integer CSX value. And also, this also needs a U32 in front of it, and PXPY also needs a U32 in front of it. Okay. Once we have the cross-section X and Y, so this looks incorrect. So with the cross-section X and the cross-section Y... Oh yeah, so we take the PX and PY, right? So we take that PX, we take that PY, and we take the cross-section, and we multiply it by U3264. Remember that the cross-section value can start at 0, right? The first cross-section index is going to be on the X or Y, will be a 0. And because that first cross-section could be a 0, right? But we're just going to make these coordinates local, right? So the local X and Y within a 64 by 64 cross-section, right? So Vx and Vy should be in the range 0 to 64, or 0 to 63, my bad. And Vz is just going to be the cross-section Y, so which floor color are you on in that missile silo, right? And... actually, I'm not sure if that's right. So let's make sure this is right. So CSY and CSX, cross-section Y, cross-section X. Yeah, because we're going to do index to XY. So we have U32 4. And this is the number of full strips plus the CSX will give us the V value. Okay, so that math looks good to me. And I'm satisfied with it. Now the next thing we want to do is this math here takes, what, U32s? So we actually want this to be kind of a... for these gets, we just want, like, the math function somewhere else. And... so we'll do, like, this whole thing needs to be a function call where we do, like, we're gonna say, like, I think IV, we did, like, IV for IVEC, right? Yeah, IVEC. Let's do, define IV3, IVEC 3. Then over here, we'll go duplicate. Yeah. So in this here, we're going to do IVEC 3. And we're going to do, we're going to do voxel 3D equals, we're going to do VI512, convert to V3D. Okay. And then we'll just put VI512 in there. And we'll make a note of what this is, right? So, V3D. And the reason why I want to separate the math outside of the functions that fetch it is I just have a hunch that this makes sense. It's also going to make it easier to test the math if we write some JavaScript to accompany this. So let's v3d equals voxel location 3D. IVEC, so IVEC3 with VX, VY, and VZ, right? So that's what V3D is, just VX, VY, VZ, kind of like packed into each other like that, right? So what we're gonna do is yeah, we'll keep this in the tile data layout section. We'll kind of like keep our sections a little bit bigger, and have like highly related stuff kind of like in the same section. So this right here, this nice function here, let's just take that header here, and let's put it up at the top here, and we'll call it U32 voxel index 512 converted to voxel 3D. And we're going to take a U32 voxel index 512. And in here we're going to do some math. And we're going to figure out what that needs to be. And we're also going to paste together, we're going to kind of bind together our functions so that we can't split them apart, right? So our divisions will be between our functions will kind of be like this. For our sets of related functions, we're just going to do it like that so that we kind of know where those bound, just so they can kind of be glued together and a little bit harder to separate when we want them to be kind of very closely related. So with this, we can take this V3D here, and I'm going to take all of this, and I'm going to paste it up here. And now we have, you know, VX, VY, and we have VZ. And this is a V3D. So what we're going to do is we're going to take IV3 and voxel 3D equals IV3. And it's just VX, VY, and VZ. So we're just shoving them all together there, right? So V3D. And then we return V3D, right? So actually, I'd like the return value to be at the top. So we'll do IVEC3 V3D. Return value. I'll do it like that so that so I'm going to write it like that so that if I hit the return, if I'm looking for the word return, I can see it right here, and I can see it right here, right? And I can see V3D here and here, so I can see it in the places where I need it. And so now we'll kind of like pack that together like that. And, you know, I'm satisfied with that. So Now we see, let's go back over to where this function is. And we only want to unpack things at the last moment where we absolutely need them. So this voxel byte XYZ, it kind of makes sense. I would rather have v3d. So let's look at this. So this voxel byte XYZ, I think in some cases we might need this, but I think we should default to keeping everything nice and packed together. So we'll do this. We'll do yeah, I don't know where it matters, where it should be. Yeah, let's make the XYZ. Let's make this function the, let's try to make the XYZ function less efficient than the one that takes a v3d, and we'll do that intentionally so that we can try to encourage the use of the v3d. So we're going to do u32 voxel byte v3d. So we're going to get the voxel byte using v3d. We'll do u32, we'll do ivec3 v3d. All done. Okay, so we kind of have a clusterfuck of stuff here, and we got to organize our thoughts here. So, conversion functions first, and then the actual fetching stuff later. So, okay, you know what? We're gonna keep this even simpler. Having more than one way to call something, I think, is just a headache. So right, having more than one way to do something creates problems. So the way we're gonna solve that is so what we're going to do is we're going to not use this function name, right? We're going to disallow that. We're going to say, gonna say do okay, we're gonna say do not use use So I think we called it v3d, right? Yeah, v3d, right? Okay, so vob v3d using right, so we want to make sure that we limit the amount of ways we can do stuff, because it's going to make the code harder to follow if there's two different ways to do the same thing, and we're just arbitrarily deciding to use this or this, depending on, oh, I feel like passing the parameters unpacked versus, oh, you know what, I'd rather put them in an object first. Let's do it this way, just because this is going to always be a more, I think, a more compact way to do it, and also allows us to merge operations together. So vx, vy, vz. So vob v3d. So let's go back over to here. And this guy, so vob xyz, what we're going to do is we're going to change this to vob v3d. We're going to take these values and we're going to unpack them, right? So we're going to do ivec3 v3d, right? And then in v3d, we'll do u32vx equals v3d dot x, vy equals v3d dot y. And then, alright, this might not be the most efficient way to write the code, but it helps refactor that a bit, right? So v3.x, y, and z, so just unpacking them. And we're just getting that voxel byte, right? So now, this v3d here, it's, we're gonna get the voxel byte using v3d. And we'll do v3d right there, right? So another thing we might want to do is not actually functions. Get So we're trying to be more, so I can see why that might be a little bit, a little bit confusing because vob dex kind of looks like the voxel byte dex, but it is get vob using dex, right? So that might actually be a little bit too terse. I'm not sure if that is going to be good, right? Yeah, that might not be bad. That might be bad. So, I think I might want to actually call it, so I don't actually think I like those. I think we need to have a clearer naming convention here. So, yeah, I don't think I like that just because I can't tell. Eventually, when I look at this, I'm going to be like, vob dex, right? Get the vob dex, but it already takes the dex. So, I think we need to name it in a way where what we're converting from, right? We can read it, it's dex converted to the voxel byte, right? So 0, if you look at this vob dex, where else is this declared, or is this the only place it's declared, right? So we're going to take, we're going to say, so really what this is, it's VI, this is really, let's name it exactly what it is, VI 512, and it's converted to, voxel byte, right? Okay, yeah, I think we'll do that. Do you want to keep this, like, OCD thing, or you just want to say T? No, let's keep C2 for convert to. Let's kind of keep that convention. I kind of like that. So this, I'm going to take 512 and convert it to the voxel 3D location. And then U32 vob, right? We want to keep the actual vob in there, right? And we want to keep the what we're returning at the very top. So U32 vob and return value. And then in here, instead of doing it as a return like that, we'll do vob equals, and then we'll do the vob 3D call right here. Right? So vob. So that way we can see that in this function, I don't want to get confused about what's actually happening. So let's try to still name the functions based on the type of data they're passing, right? Because all we're doing is transforming data. So let's write the code to make it very obvious that we're just transforming data, right? Looks like that is for tomorrow. Today is 6:30. I think, did I say 6:30 appointment? Is that correct? Am I going backwards? The 3rd and the 4th, right? And today is the 3rd? So So let's look at, I'm going to look at my Gmail really quick, make sure that I don't have anything going on. Yeah, I think today is... So, December 3rd, and if we look at this, appointment reservation, 2 hour, 6:30 p.m. Yeah, so 6:30 p.m. today. Okay, so we're good. We can keep on going. And let's look at this code here. So we're going to take the 512 and we're going to convert it to the VOB object. And I think we need a little bit of space there. So the VOB, VI512, convert to the voxel 3D location. So, right, so just this is the conversion math. Once we have the V3D, we'll do VOB V3D. And VOB V3D, same thing. What we're really doing is we're taking V3D and we're converting it to the VOB value. So let's take that, and I'm going to say that I actually do not like that function name. So, so anyway, where we have functions that are not actually functions, I'm just going to say, well, what should we actually use? Alright, we're going to do that. So, and then VOB dex, rather than VOB dex, we're going to use right. So we can take a 3D value or an index value, and we can locate that. We can get that voxel byte, right? Right, and then so the problem with writing it this way is that these functions get really long, but the function name is based on, exactly what data is being passed back and forth, so that's kind of why I'm doing it that way. So let's go back to where we're already refactoring stuff, and we haven't even ran the code yet, so, so over here, this is, we're taking v3d, and, we're gonna convert that to the byte value, right? So, v3d c2 voxel byte, right? And this byt should be called voxel byte, because that's what it is. And then we can take away that U32 there, and we actually want to put what we're going to return at the very top, right? So U32 vob return value, right? Okay, so we return the value from there. Okay, so now the next part is we have conversion functions up here. So we have like the 512 converted to v3d, and inside here there's some type of conversion going on where we're taking v3d and we're converting it to PXY 256, right? That's what we're converting that to, right? So let's go up here and go, and this isn't a 3D, this is a IV3, right? Because IV3, so V3D right there is a IV3. So we also need a IV2, and we're going to take V3D and convert it to PXY 256. So IVEC 3 V3D. Right. So we have a PXY 256, which is a pixel XY location on a 256 by 256, right? So we can make a note of that, what that is. So we already have PX. So PXY 256 is IVEC 3 with PX 256, PY 256, right? So that's just the range of what this is. Okay, let's go back. So now we have this conversion function, and we're looking at all this V3D here. So we have a texel fetch, but there's another thing we need. We need the cross-section color, right? Because to get that byte color, we need the cross-section color, right? So X, Y, and C. We actually need X, Y, C. The X, Y, and the channel is what we need, right? So let's not do it as PXY 256. Don't use. use XYC256. XYC256 is going to be IVEC3, and it's going to be PX, PY, and then the channel information, right? So this CSC, right? Cross-section color. So XYC256 is what we're going to do there. So over here, where we have this function here, it's going to be v3d convert to XYC256, and we'll do a IVEC3 XYC256, and this is the return value, and then we'll do return, and then XYC256. Okay. If we highlight that, right, we have the exact thing we're returning, and the name of the parameter we're kind of converting, right? We're transforming, all we're doing is transforming data from one thing to another, right? So we're transforming this, and we're converting that into this, right? So very simple. So with that conversion function, all this crap we were doing, before we do that Texel fetch, right? There's this Texel fetch, so all of this we can take and we can put that into here, right? So v3d xyz, right, we're going to unpack all of that. And then right here, we're going to do the same thing. Before we return this, we'll do XYC256. Dot x equals px. Well, let's do what's ever shorter. Let's not worry about over optimization. So XYZ256 equals IV3 PX PY and our CSC cross section color. Okay. And then we actually need to call that, so over here we'll do v3d to XYZ256, XYC256, and we'll take that v3d and we'll just plug that in there, and then we'll do IV4 or IV3 XYC256. Okay, so this XYC256 equals converting the v3d to the XYC256. And once we have that, we got to just unpack. So U32px equals XYC256.x. U32py equals XYC256.y. And U32 CSC equals XYC256.z, right? So 1, 2, 3, those three components are kind of packed in there like that. PX, PY, and this cross-section color, right? Because when we get the color 4D, we gotta do that. Now, color 4D is not the voxel byte color, so that works there. And then we're returning the voxel byte color there. So that looks all correct, right? So that was a lot of extra stuff, but the thing is that we want these conversion functions first, and then we want the actual fetching second, right? Because the fetching is pretty simple, right? If we take this index and we just want to get the voxel byte, then we want to take v3d, and so this v3d, that no longer exists, so we're getting voxel byte using the v3d. So there's only one Texel fetch for this, right? Yeah, okay, cool. So v3d convert to voxel byte. Okay, so we'll take that. So v3d convert to voxel byte. And that's good. Like I said, I don't know if we can actually access values like this, so I kind of left that out. So since I really don't want to, have to write this code in JavaScript to test it and make sure it's correct. So with this buffer code, do we still have the main function? Do we still have that main functionality there? Yeah, and we haven't even touched the main functionality. We've just, oh god, I saw a shader with the common, and then I don't know where I got that from. Let's do, I'm gonna look at my shader toy history for a second. I'm gonna put that in another window here, because I know I saw a shader that had, like, a common stuff. So let's, I'm gonna look at my history and see if I can find, because I saw somebody use a common, and I thought it was interesting, but I kind of ignored it. Okay, yeah, so this stateful particles has a common. And is common like a... Common might just be a... So I'm going to take this, and I'm going to put this in my notes. So there is a... shader uses common. Common tab. Shader toy common. So this shader has like a common thing, and I think that we definitely actually need some type of common code that we can paste into both of our shaders, because we're gonna need this kind of logic for both of the writing and reading is both going to need these conversion functions. So let's see if there is a way to do a common tab. So I'm just going to do a so this stateful particles thing has some type of common tab. So I just want to see if we go to the new tab here, is there kind of a common thing that's kind of like injected into both of your tabs? Like, how does that work? But being able to cut and paste our code from one thing to another would be really helpful. So let's see what we have here. So down here, let's see, we have a common, right? And then yeah, so it's just called common. And I'm going to take a guess that we can use common inside of here, and it'll just work, right? So let's try that. Let's try something really simple. Let's try define I don't know, define R as 1.0. I don't know, define G as, can you even see this? Can you see this? So define R as 1.0 and define G as, 0.5, and then define B as 0.1, right? And maybe we'll do A as well, right? So define A as 1.0. Okay, and if we put that in common, and then we just do screw all this, right? Let's just blast that away, and we'll just say that frag color equals RGBA, right? And if we do that, we get orange. Okay, so there is kind of a way to use common. So I'm going to common. Includes So, hashtag include code in multiple files. That's kind of, my understanding is that, common tab can be used to create code that is hashtag included in all of your other tabs of code. Right? So that's my understanding of how that works. And we're gonna keep that as a, we'll keep that as unlisted, I guess. And then we'll kind of like submit that. And then I'm going to take this to, I'm going to put this in my notes. I'm going to say my common example. My common example tiny URL. Okay, and then we'll go to tiny URL and just add that, right? We'll call it, we'll take it and we'll call it, shader toy include, right? So we'll call it shader toy include. And so if you want to go there, just tinyurl.com/shadertoyinclude, and it's unlisted, but that's how you would get to it if you wanted to look at that example. It's pretty trivial. I don't think you would need to, but it's there. So we really want all this code in a is kind of like common code. So this is great because now we're like getting kind of like functionality that needs to be in both things. And oh boy, oh boy, oh boy, right? So first thing we're going to do is we're just going to take this buffer and we're just going to paste it into the buffer tab, and we're just going to get it working first, right? We're going to make sure that there's no syntax errors, which I assume there are plenty of. And it's doing that again, so I guess we got to go back and forth between both tabs before we see the errors. I guess that's just the way it is for now. I don't know why it's doing that. So cannot convert from high P int to high P uint, right? So if we look at, Gaia, so I've been using, the X, Y, and Z should probably be, Texel's fetch uses integers, so I think that, the, VX, VY, VZ should be signed. So in 56, let's go to 56 and kind of change some of our logic here. So in 56, is this buffer? Oh, it's like at 59. Okay, so these U32s, we're gonna say that those are gonna be I32s. And VX, VY, So Pixel X, I'm gonna make those. I'm gonna make the Pixel X a I32. It looks like it's already a I32 here. And VX, VY, and then we see this. So it's just going to be a lot easier if a lot of this math is just int 32. Yeah, I would rather just convert all this to, rather than have some extra casting problems, I think that we just convert all this to I32. I think that would be better. So I32, I32. Right, and this is also an integer by default as well. So, I32, I32. Right, I think that just makes more sense. And then PX and PY, we don't have to do anything fancy. And the CSC, also I32, so they're all compatible with each other. And then we can just return it, right? And then we can look at where else we're using the, and this is not a IVEC2, this is actually a IVEC3. And let's look at where else this is used at, right? So IVEC, so this, so IVEC3, so yeah, they're both IVEC3s. But PX, PY, these are all going to be I32s now. And voxel byte needs to still be a byte value because it is an unsigned integer, so let's not wreck that. Index accessor, we can do that. That looks good. Right, and then we return the voxel byte. Okay, so that looks good. U32, voxel byte. Okay, yeah, let's take that and see what other problems that has. So let's paste that into the buffer. And switch tabs back and forth to see what kind of problems are going on. And multiplication, wrong operand types, no operation exists that takes left-hand operand of int and float. So we're mixing int and float here. So I see what the problem is. I wish that would just be something we could implicitly cast, but whatever. So in 73, it's saying that right here. So CSL is an I32. So since this is whole number math, it actually makes sense that this would just be a 4, right? So it is just a 4. And I just want to put it around in brackets so, you know, I know the difference between this 4.0 and that 4.0. So we're just going to keep on trying this code out until until we get rid of all the problems, and then we'll probably put this in a common section of code. So cannot convert from high p int to high p uint, so then 92. So px 512. We really want to keep those. So all this stuff that's U32, we're probably just going to do I32 for signed, unless it's a byte value, right? If it's actual location on the canvas, we'll allow that to be negative. Allow it to be negative, right? And negative is just an invalid value. But if it's a texture location, I'm not too worried about it. But if it's an actual value that can be encoded into a pixel, then I'm worried about it. So let's change everything to... so we take this 512, convert it to I32. It's already a I32, so you don't really have to worry about that anymore. So this VI, right, so this is going to be I32 as well. And the quadrant, yeah, we'll keep the quadrant as that, and true, but not needed here, so we'll keep that there for reference. Yeah, so I32, we're going to just change everything to I32 unless it is something that is a byte value. If it's not a byte value, we're just going to keep it as I32. And then voxel byte, right? So that still needs to be a U32 because it's a byte value, right? Let's see what else we got wrong. So we're mixing and matching something on 105, so let's see what we're doing wrong here. So CQX, I32, and we're multiplying it by a float, and that's no good. So this is whole number math. We don't need to do the 256 point whatever, right? Now when we're dividing, we have this pixel X, pixel Y thing, and we're truncating the math, but it starts out as an I32, so this also needs to be converted to float 32 before we divide it. So we got the X's and the Y's, and let's give that a shot. And then after we get this working, after the code no longer crashes on us, we're going to take a quick check to make sure that, like, we don't have any XY transpositions, because that is a source of contention for me. So 165. No matching overloaded function found. So that tells me I probably got the sign wrong. Yeah, so this U32, we changed that to I32 for the index. And let's take that and give that a run. Okay, it went green. Cool. So I expect no difference in the behavior, right? Same pixel setting stuff. But now let's take a quick pass over looking at the X's and the Y's in this code and making absolutely sure we didn't, like, make any mistakes. So let's do VX, VY, VZ, and we have X, Y, and Z, right? So those colors match up. So we have Y's. Let's just do anything that's a Y. So Y's and X's. X and Y. Right, we just want to make sure that X's and Y's are being used correctly with each other. This is something else. The cross-section color is kind of like a Z, but let's just make it purple because it's kind of like a different kind of thing, or I guess it's green. So that looks like we didn't make any blatant mistakes. So if we look at this, X, Y's, index. The index, the first thing we can get is the Y, the X is the remainder when we use this type of formula. X's, so here's X's and Y's, so let's color those X's and Y's, make sure they match. X's, Y's, X's, Y's, X's and Y's. So we're using a index to XY to index XY formula to get the VZ. CY times the rows are 4 long in our diagram, and then add CSX at the end. That makes sense. VX, VY, VZ. Okay, so over here, let's color code these. You know, it might be obvious, but the thing is, we gotta be redundant like this. So that's interesting. So CSC, so the cross section is kind of corresponding to the Z value, so that's sensible. PX, PY. And interestingly enough, this just didn't crash, so I actually think this might be the allowed way to do it. Yeah, so I think that in terms of that, I think that we have X, Y, Z, W. I think we're good there. Let's paste that in there again, make absolutely sure. Okay, cool. So now that we have that, what we want to do is we want to take all of this kind of code, and we want it in a common section, right? So this kind of sucks that we have even more tabs, but let's just do it. So let's keep the same kind of header thing, right? Do they all have instructions? Yeah, they all have, like, the minimal instruction, like, header there. So let's take this file, and in this new tab, we'll do this, and we'll S19 in common, right? It's the common. All of this stuff is kind of the same. With the macros, right, we undefined them, and I believe the section header for macros and undefined looks exactly the same. So we can take that, and then in our common code, we'll kind of, like, do this down here. And then, data. We'll keep the data section, right? Data, then functions, data. And then we have functions. Right, and the functions we're not going to indent. Okay, we got this data section, we got the func section. So SDF 019.common._. So this is annoying. This is so we're going to do it cbids, right? So so source code common, right? And we'll do tinyurl.com/sdf-019 and common, right? And so this is kind of like ridiculous, right? This is a live so we're gonna separate these chunks a bit in here. And we're gonna put the live demo at the top. So common, buffer, and image, that's kind of like, boy, this is just a lot of resources. But I think it'll pay off if we're organized, so let's just keep on doing it. So now that we have this kind of header, right, live demo, setup video, in our image, right, we'll go over here, we'll paste that, and then in the buffer code, same thing, we're going to paste that. And then in this stuff here, right, we're going to have we need to add source code common into here. Okay, so we don't know what that is yet. Source code common, and I think the most important things are so I think taking the live demo stuff and separating that a little bit, right? So we have our easy URLs, our direct URLs, and then we have all this other stuff. So, we don't really need, can we get rid of the source code and just be like source this, source that, right? Can we just make this a little bit, the reason why I want to shorten that a bit is so that we can do that and get a little bit more sensibility into the way we are kind of like some indentation would be very helpful right now, right? Then we can do D like that, and we can do D like that. So now we kind of have a nice hierarchy where we got the easy URLs, and we have the live demo, setup demo. And so the most important thing is I want to see what your code looks like. Then I want to see that, right? This is the order in which I want to see things. So now let's take this, right? This easy URLs, source common, source buffer, source image, documentation, right? We're going to take this kind of, these easy URLs, and we're going to paste them into kind of like this stuff here, right? And we don't need the header that says easy URLs. We can just, oh god, where am I? We can just paste it directly in there, right? So So actually, for this one, I'm going to do code common, documentation, setup URL. And then one, two, three, four. So that is correctly indented. I don't know, that's kind of weird, but you know what? Let's just keep it like that. Buffer. Right, because we have some type of hierarchy here, which I like. And then in common, we can do the same thing, right? Common. Right. And then in our kind of like other stuff, we can kind of keep it like that, maybe. Yeah, I like that. That's good for now. Let's, I'm kind of annoyed by how complicated this is getting with, like, all the different files, but, I think it's for the best. So let's, take, the common code and it's all this tile data layout stuff, so let's just take it and let's paste it into common. Okay. And now let's take the buffer code first, and let's paste all that. And then we're going to add a common tab. And then in our common tab, we'll take all this common stuff. And also, did we label it properly at the top? Yes, it's labeled properly at the top. Cool. The self URL is not that. It is common, right? Common. This self is it buffer. This self URL should be buffer. And then does this have a self URL as well? Self URL SDF019. Okay, yep, so that's good. So let's take the common code and let's Control A and let's paste it there and hope that our like weird defines and undefines don't like fuck with us. So seems that we have some type of problem. So iChannel 0 undeclared identifier. So I might not understand what is allowed to go into common here. And also there might be so it looks like common doesn't get to have that kind of stuff. Okay, so Texel Fetch probably exists, but then the iChannel, we can't do that, right? So, what we're gonna do is, since we can't hard code that channel anymore, that's fine, right? We just have to think about how we're gonna rename or reorganize our functions here. So let's find the thing with the textile fetch. And right here is textile fetch. And or this is the function of the textile fetch, and it is so really that's like a when you use textile fetch, the first parameter I believe is a sampler, right? So let's look at that for a second. So textile fetch, I believe the first value is a sampler. Yeah, sampler. So what we're gonna do is this needs so we're gonna call this we're just gonna call it Sam, and then in the function, or we call it v3d, we're gonna call it v3d and Sam, and then I believe the sampler should be like I believe the channel value is just an integer, I think. So I think the sampler just needs to be like that. And then anywhere that's used, let's just... Okay, so I think that's how it needs to be done. So let's Sam equals I channel 0 and shader toy. Okay, we can make a little note of what that's supposed to be. Okay, so we'll take that common code that we've kind of changed a little bit, and we'll see if that corrects the problem, right? Or if there's something more. And oh boy, we have some mistakes. I don't know what's going on. Oh god, everything's red. Not cool. So let's see what we can find for iChannel. So iChannel, what is iChannel, right? Like, what is iChannel? So let's look at iChannel. iChannel shader toy. What if we just put a... Okay, so let's say in this example shader, what if we just take a 0 and we put that there, right? Texture, no matching overloaded function found. XYZ field requires structure, vector, or interface block on left-hand side. So it looks like 0. Let's try a 0.0. Let's just try, if we try a U32. So it doesn't think so. It looks like it takes a struct of some sort, so I don't know exactly what I32 is. Okay, so I channel 0. So I channel 0. Okay, so I channel 0. Now what about, I know it says it's like a sampler, G sampler 1D SAM equals I channel 0, right? Is that what we gotta do? Well, actually, it's a 2D, so let's try that. Let's try sampler 2D. Oh, did that lit up? Let's sampler 2D. Sampler 2Ds must be uniform. Okay, well, one more thing. So we have that, but can we... If we put it in a function, will that change things? So, if we do vec for get frag color, okay, so we can take it as a sample. We can take it as an argument, it looks like. Okay, so that works. So we need to call it sampler 2D SAM, right? Okay, got it. So we can still make this work. But the SAM here, SAM needs to be, it's a sampler 2D, like that, right? So back in our common tab, right? We're in the common. Let's take this and go Control A, Control V. Just run that. So now, same thing, we're going to have to take some stuff and we're going to have to change it around. So this thing that was this and then just nothing, now we need to include SAM as one of the inputs, and so sampler, it's just called sampler 2D. And then we might want to take this and do S2D for sampler 2D, so it's not as verbose. And then this thing no longer exists, right? It's now like a I don't know, this is still a conversion function, but this V3D CTO thing, right? That's no longer there. It's V3D SAM. Right? Okay, yeah, so that's what we're going to do. So save that, take all that, and then we're going to paste that in the common tab and see if that will work, right? Or see what other mistakes we made. No matching overloaded found. So 161. Well, that's because we need SAM as the second parameter again. So we're going to pass SAM down. Okay, now we got something that is no longer crashing on us, right? So let's hit the save button on that. And I'm going to take this snippet and I'm going to make a new shader. So I'm going to do new, leave. We'll make another unlisted shader. So we'll just paste this here. And then we'll play it. Or, we'll make common, and then in the common, we're going to take this, and we're actually going to throw it in the common. Right? So let's take this, let's make this UV. Let's move this out of here, and let's say UV and UV. Give that a run. And this is not iChannel 0. Why did I say iChannel 0? That should still be SAM for sampler. Okay, cool. I just realized that there was something in that shader that had display iChannel 0. Let's check out this thing. So Okay, so this is some type of music here. How the hell did they do that? Um... Let's go to... Oh, I see. God, that's not very friendly, is it? So it popped up, but it just didn't pop up where it should have, and also... Okay, so, you know, we just can't do... This UI is not friendly for small screens. So, textures cubic, so is music... And if you take this music... Okay, got ya. Okay, got ya. So, over in here, if we want to do that, we got this common in this, and then if we want to actually, in our image, I don't know if we could do it in common. Common doesn't have any tabs for channels, so in channel 0, let's just go over here. Let's get some... music. Interesting, okay. I have no clue how they're storing the, it's a version of setup requires you to click channel 0 below the when. Um, we'll keep this one as unlisted as well. We're gonna let's actually see if we can change this to Texel fetch, right? I'm gonna guess it's gonna break because we have yeah, let's not worry about that. Let's just keep it as texture. That's fine. Okay, let's put that into www.tinyurl.com. And we'll do reusable texture fetching code. Reusable texture fetch. We'll take this, and really what we're doing is we're using iChannel, and we're using it in the common, right? So iChannel channel common. We'll just call it channel common. Right? Channel common channel iChannel common iChannel. Okay. Okay, and if we do channel common, tinyurl.com/channel common, right? Okay, that's good. So now we have like a little example of how to do that, because I was a little bit confused at how that works. So we can close that. Yeah, we can leave that. So we have our code, we have our common stuff. Oh god, now that blacked stuff out. So okay, so if we resize our canvas, there is the potential for everything to blow up in our face. That's fine. We kind of know what the problem is, and you know, we can address it if it happens to us, right? So we have a lot of stuff. Let's take everything, right, and let's copy paste it again. Just make sure that everything is up to date. And then this is our image. Okay. And then let's take the buffer, right? So copy that. And we'll do paste that, and we'll paste that there, right? And I need to it's gonna be pretty soon. Pretty soon, it's gonna be time for me to head to the machine shop. So I'm going to take what I currently have, and we're going to make paste bins for all this stuff because I know I didn't earlier, and we can reference old code. SDF17 is the voxel marching first attempt. Voxel march first attempt. First attempt voxel. Voxel first attempt. First voxel. Voxel first. So, we want to make sure that we know that SDF17 is kind of the first attempt where I tried to do this voxel marching, and we kind of decided that we had dug ourselves into a hole, and we wanted to like rethink about how we were going to do this, right? So we want everything to be in terms of pixels, right? To keep everything simple. We want all of the math to be in the global coordinate space, also to keep things simple. And so when we're passing around values, I always want them to be global location values, and I always want those values to be in terms of pixels. Sometimes that might not make sense when we're talking about like a voxel or a bounding volume, but I don't want to have to deal with global and local, and I don't want to have to deal with different types of units. The more standardization and uniformity we can have, the easier it is going to be to do this and not have any mistakes. So let's go to www.pastebin.com and let's look at our documentation first. So it looks like we have a documentation URL already for this, and it looks like we don't have anything else for all the other stuff. So let's go to the documentation URL, and let's update that. So we're going to update the documentation URL, and I'm going to hit edit, and we'll add the documentation URL stuff. Make sure it says SDF19. Good. And we still need to do stuff for the other things, so we'll have to update the documentation URL one more time. But let's take this buffer code, and I'm going to do a new paste here. I'm going to paste the buffer code. And we'll do paste name as title is SDF-019 buffer. And syntax hiding is GL shading. And we'll create that. Okay, now that we have that one, we can take this for the buffer and go to our documentation thing here. And we have source for the buffer is right here. And now we need to create one more paste, so we're going to create another paste. And we're going to take the image, so take this image code, we're going to paste that in there. The syntax highlighting, we're going to do GL. And this is the image code, so let's scroll up, make sure that it's the image code. Yep, we got the image code. So we'll do SDF-019 and image. I'll create new paste. And with this image code, we'll take that, and we will put that in our documentation here. So our image, and then our so a part of me just wants to be like, screw this, just put it on GitHub. We could have a GitHub URL for this as well. But I just want to keep it as something that's like really easy to keep track of, right? So what we might do is the nice thing about doing it this way is just that by locating all these resources, we don't have to worry about the complexities of the version control and whatnot. So let's just keep on doing this, and we'll think about our ways later. So in the source code common, we're going to take this, and we're going to do a new paste. And we're going to go Control V, and this is the common stuff. Syntax highlighting is GL. And SDF 019 and common, right? So this is the common. All right. So this is very hackish. I think I would like it to be where there's just a, do we want, like, individual GitHub repos for all of the SDF stuff, or do we want it all together in one? I think it should all be together in one, so people can kind of reference everything as they're doing it. I don't know. Okay, but anyways, we got all those URLs, so what we can do now is we can take this common, right? The common, SDF common, and we can just make sure that everything is there, right? So www.tinyurl.com, and in our documentation, SDF common, okay, SDF common, and SDF 019 and common. Make tiny URL. Okay, and then let's do documentation should already be here. So tinyurl.com/SDF019, right? That's just what it is for documentation. Or maybe we don't have that, so we're going to take the documentation URL here. And after this, I think we're going to not do it this way anymore, because this is just out of control. I think it would just be better to have, like, it on GitHub and just let people download, like, all of it, right? Yeah, I don't know. I don't know. The more stuff, it's harder on me, but it's easier on people who want to be able to look at this stuff, right? So here's the documentation URL. And let's do take it, and then we'll do SDF 019. Okay, SDF 019 was created. How about the buffer, right? So the buffer. So here's the buffer code. So we'll do enter a long URL. And we'll do SDF019, and this is our buffer. Let's make absolutely sure that's the buffer code. Yes, that is the buffer code. Okay. And source image, same thing. Let's do so we'll take this source image code and we'll also put this on pastebin. So that's the image code. So we'll take that and we'll do SDF019-image, right? Okay, so now we have like all of that. And in our common documentation, we still don't have, do we have a tinyurl/demo? So tinyurl.com/sdf-019/demo. Do we have that? Yep, and we have the demo URL already. So let's go to tinyurl.com/sdf-019. Let's go to the documentation here. And let's edit all of that. Since we have these URLs are now kind of figured out, we can go into here, we can go edit, and we can paste that, right? And we'll do save changes. So yeah, this is really annoying. I feel like we might want to set up a GitHub repo for this kind of stuff. It's just getting way too annoying, right? And we can actually move we can just move all of these files to our GitHub repo, and we can just call it SDF, so git/SDF. And we can make a little note that these files were moved. So I think that's actually what I'm going to do right now, just because we don't have much time before I have to go to the shop. So we're going to just take some time to organize ourselves and just organize our thoughts. And the first thing is, if we do that, all these things that are SDF whatever are going to be needed to be refactored in the code. So let's make a little to-do here. So to-do. And so where we see SC files, my shade needs to be converted to R drive, git. And actually, let's see how much memory we have on our R drive right now, because I know we're running out of room. Properties. 441 megabytes. This is just text files, so we should be fine, but we are running out of room. So okay, so we're going to close that, and let's go back to our OBS, and okay, so in here, let's go into Git, and let's make a folder called SDF. And actually, we're going to call it, rename, we're going to call it SDF 2020. And the reason for that is I've decided that we need to start tagging the repos we make with the date that we initially created them on, just because we're making a lot of repos, and it can be kind of hard to like remember where everything was, right? And also, we should probably call it 2020 SDF, right? So that when we're sorting the files, we can find it. Or no, it's going to be easier when we try to go out to the files. We probably want to be able to find. The most important thing is to be able to find what we're looking for. So SDF first, and then 2020. Also, we can't use 2020 SDF as a namespace, anyways. So we're going to stick with SDF 2020, right? And we're going to take all of the files that we've had and in our shader code stuff. And we're going to cut and paste them into this SDF 2020. And do we just want to keep it like a linear folder of stuff, or do we want like a README? Yeah, let's not get too fancy here. We can always fix this up later. Alright, so we're going to paste that, and we'll go git bash here. And,
Jamie, if you want food.
Okay. So, we'll do a git init dot. Okay. And look at git status. Git commit -am. First commit, git status. Hold on, git status. Oh wait, git add dot. What am I doing? Git status. Okay, now git commit -am first commit, right? Okay. Status. Okay, so now we're gonna go to GitHub really quick. So www.github.com, and we'll actually make this one public, right? And we'll do a new repo. We're gonna call it SDF 2020. So SDF 2020. And the description is shader toy live of me working on this code. Okay, and we can keep the same thing where it's like we open up. So we can do this and live stream of me working on this code. We'll keep it public. And we won't add a README, and we'll create this repository, right? Okay, that looks good. And yeah, this screen wasn't really meant to be for GitHub, so sorry about that. This kind of sucks. Okay, so with Git, we have this Git URL. I'm going to want this Git URL. So I'm going to do, in my shortcuts, we're going to do SDF 2020 Git URL, SDF 2020 Git URL, SDF 2020 get URL, and SDF 2020 get URL, and SDF 2020 get URL, right? So just the get URL, that's the most important URL. Screw every other URL. So with that, we can go over here, and we can do git bash here, and we can open up. Actually, it might be easier if we do it over here. Let's see, can we kind of center this? Let's figure out where the center of the screen is. So yeah, we can kind of get this over here where most of it can be seen. And we'll do git status. And then git remote -v, git remote add, and we'll call it GitHub like that. I just do that so that I know it's my variable and not like a built-in. And then we will paste the URL for that GitHub. Git remote -v, git push GitHub. So it doesn't know what branch to push to. We're just gonna push. We'll do that, fine. Because I don't want to have to say git push master all the time, or git push GitHub master. I would rather just do git push GitHub. So we'll do that setup step, and then that'll be on Git, and they will kind of like clean up the code there. So I think from now on, we'll just, we'll go back to having one little tiny URL, and it will just be the, right, we'll try, yeah, because it's just getting way too complicated, so, yeah, it's just too complicated. So if we look at, if we refresh our GitHub, we got all these first commits, and we got these, different SDFs, right? So you can see where they are and how to use them. Got it. So I think that's good for me. And about live stream of me working on this code. So yeah, let's just keep it like that for now. And SDF 2020 web URL, SDF 2020 web URL, SDF 2020 web URL, SDF 2020 web URL, SDF 2020 web URL. And then if we just do SDF 2020 URL, or SDF 2020 URL, SDF 2020 URL, SDF 2020, SDF 2020 URL. And if we type that, then we'll say pick SDF 2020 web URL or SDF 2020 git URL. Okay, and then we want to reroute anywhere we see my shade. We're just going to do r/g/SDF 2020 /SDF 2020, right? That's what we're going to change all of these paths to. Anywhere we see this, we're going to change it to this, right? So that we refactor those shortcuts. So it opens the new stuff. So we'll do r:/SDF 2020. And let's just find everything we reference. So this is going to be a lot of stuff, is it not? So let's actually put another backslash in there so that we can change this to all forward slashes. So, okay, let's get going. So r:, let's make sure this is absolutely correct before we do it. So r:/g slash SDF. Yeah, okay, yeah, so SDF 2020. Okay, yep, let's do it. So let's replace that. 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 That. Let's replace that. Let's replace all these kind of shortcuts in our source code, because now we have a we have a new kind of way we're gonna store all of that stuff, right? So done. And let's make sure, one more thing to do, and there's always the possibilities that it's scfiles/math/sdf/my_shade. Like, that is also something that could happen. So we'll also look for this as well. Let's make sure that we didn't miss that. Okay, looks like that is done as well. The next thing is, let's look for anything that says my shade and make sure that these are the only two instances. So SDF folder. So this SDF folder is now not going to be my shade anymore. It's going to be full file path to clipboard. It's going to be, and it's just going to be paste line, right? No more paste line expanded. Okay, so let's look at where else we have kind of this this my shade stuff. Yeah, so that's the only place where we have that stuff. What about math/SDF? Is there anything else where we're doing that? And okay, so those are like snippets. The snippets are fine. Yeah, the snippets are fine to keep where they are. And then let's take our, let's go to our old SDF folder, and let's just nuke everything, right? So that is kind of nerve-wracking, but let's actually do this. New folder, and we'll just say delete this moved content. So we're gonna, before we delete it, we're gonna just say cut and paste file new, and then we'll make a moved to RGSDF 2020. And actually, we could do this. Moved dot to, right? And then we'll just make a note here of where this is moved. So all of the code that was in this repo was moved to its own public repo. To do. Once enough time has passed and we think it is safe, delete folder. Right. So once we think it's safe, we're gonna actually delete all that stuff. New location. Okay, that's good enough. Just a little we have moved thing in case we accidentally end up in this folder again. And that way we just know where that has been moved. Now the next thing is that we want to go Control F SDF 019 and see if we have any shortcuts for SDF 019. It does not look like we do. So SDF 019, SDF 019, do we have a underscore 019 maybe? Try edit SDF 019. Okay, so with SDF 019, there are like multiple files. So if we actually, let's do this. So we'll go File, Open over here, and we'll take this folder location, paste it in there. And we'll take all of the SDF 019 stuff. So all this stuff, we'll open it up, and full file path to clipboard, edit file, full file path to clipboard, edit file, okay, so we're gonna do AutoHotkey folder, shortcuts, SC files, and then in openers, we'll have SDF 2020, and in there we'll do SDF 019, right? So this will actually open up SDF 019. Invoke file contents. Okay. Invoke file contents. SDF 019. Okay, cool. So that's just so that we have a way to get back to all those files that we were working with, create like a nice little save state for us. And we'll worry about maybe adding more details to how we're going to we have to figure out how to make sure that our conversion code is correct. And I think the best way to do that is we're going to take a canvas and we're going to run we're going to take the let me think about it. So we have do we have a 512 right now? How do we get that? Interesting. We're going to make a shader, and that shader is going to do an index to XY, and it's going to do a 512 index to XYZ, and then it's going to do an XYZ to 512, right? And we're going to make sure that the conversion back and forth is always 0, right? And the way we're going to confirm that that is the case is that our shader, we're going to use the shader code for that, and our shader will just be completely black if there's no errors in the calculation, and if there are errors in the calculations, one of the pixels will have non-zero colors, right? But before we do that, we have to, let's look at our code now. So let's look at our SDF common code. And do we even have that? So we have the XYZ to this 256 here. And so really only texture fetching should use this function. Okay, so only texture fetching should use this function here. Right? So let's look where that's used. And indeed, it is using where we're doing like a texel fetch. And the reason we want that only there is because we have these other conversions where we have like a 512 to this v3d here. But I don't think we have the opposite, right? Yeah, we don't have the opposite. So what we need to do is we also need to create a v3d to the 512 and make sure that we can convert back and forth between these two things properly, right? So over here, we're going to do it's going to be I32, right? Because we're going to take so we're going to take v3d and we're going to convert it to the 512 value, right? So we're going to try to keep all of our math pretending that we're using a 512 by 512 texture. And because of the way I would like to eventually do this in some C code. But first we just want to get it working in ShaderToy, and then we'll kind of go from there. So v3d, we know that that's the IVEC3, and v3d stands for voxel three-dimensional location. And then at the end of this function, we'll kind of glue this function and that function together again. I don't know how we want to do that. Do we want to like glue it right on there like that? I guess we could. Tile layout data. Okay, so in here we want to kind of figure out the math, but we are probably, I probably have to go soon. I probably should get going now. So over here, to do Vx or Vx, Vy, Vz to Vi512. And the idea is that only in our private code should we be using the actual texture dimensions, right? We want to pretend that we have a 512 by 512 texture, and later when we have more memory to do more things, then we can just expand things out, right? And so I'm going to actually make a some notes here. So we have some documentation, right? So let's go to our documentation section here, and let's say extra maps. Once we are actually using a 512 by 512 texture, we will have 3 extra maps worth of data. I think we could do it like this. map 1. Original voxel map. Map 002. Lighting map. Map 003. Sprites or other moving entities. And then map 04, elemental things, fire, water, etc. So this is what I'm thinking, what we might be able to do with all that extra data, right? So sprites, you could have your player and whatnot in this slot of our voxel map. Elemental things like explosions, fire, water, etc. The lighting map. So a lighting map that kind of calculates some pre-baked lighting and how that lighting is going to interact with the voxel map. You could put that on that layer, right? So you could have these, you could use these extra slots to create these different layers of things that would be good for a game, right? And that way we can keep everything to this nice buffer. And yeah, I think that's how I want to do it. So we'll just do this like that and call this extra maps. Okay. That is a good stopping point for now, where we've kind of collected our thoughts. You got these ridiculously crazy diagrams where we got like more documentation than actual code. But we're going to try to be like really careful with when we're writing this code. And we're kind of try to be like super terse. We're going to try to be like ultra terse with our code. And this needs to be done, so let's just do hashtag error finish this. I think if we do that, that will, if we put this into common like that, it'll definitely blow up in our face, but I don't know if it'll blow up in our face in the way I think it should. So let's compile that, and okay, so that looks good. Let's fill out some of the things that need to be done. So, VI 512, right? So at the very end, we just want to return that VI 512. So we're going to do return VI and then 512. And then at the top, we'll declare what that is. So that's an I32 VI 512. So that's a voxel index 512. And we'll just say that this is return a value, right? We'll say it's the return value, so when we double-click return, we can see it highlighted here as well, and so we can see that connection. So the connection between the input and the output is very obvious. We could save a little bit more space. We could put that I32 right there. And yeah, I'm good with it like that. Let's copy and paste that and see what the error is now. I'm hoping that the error will eventually just say that the error is finish this, right? Error to do finish this. So that's good for me. I don't know if that's actually just understood by the compiler or whatever, but that's good enough for me. So we're going to save this and just keep that error in the code for now. And okay, it's been 3 hours, so I guess we spent the time well, because it was... That's a decent chunk of time. And 6:30, yeah, so I can get going now to the shop, and I'll be to the shop in time, and I can start cutting some stuff that I was working on, and hopefully if we just keep on plugging away at this, we'll get back to where we were with SDF 17, but then we're going to exceed that, right? So because we're going to make a generic voxel marching algorithm. I'm sure we're going to have a lot of headaches along the way where we have errors. We'll have to debug, figure out where those problems are. But hopefully, if we're careful and we double check stuff, we'll figure it out and we won't shoot ourselves in the foot. So we're gonna keep on building in SDF 19 until we have like something where we click, and instead of just putting down a pixel, we're putting down tiles, right? Because we already have the SDF www.tinyurl.com/SDF018 demo, right? We already have this demo, right? Yeah, we already have this demo file with the buffer and the image, so we want to kind of like build up to... we want to build on top of that, right? We want each file to be uniquely different. So we're going to keep on building on this until we can figure out where to go next from here. So let's keep it up and see if we can make some progress. We're going really slow. Hopefully I make something awesome before I die, because holy crap, I'm taking forever to do all this stuff. So let's check our notifications and stuff. Unlisted. Alright, yeah, I think we're good to where where we can kind of... Yeah, I think we're good. Let's wrap this up. Let's get out of here. And we'll be back after, so 6:30, 7:30, 8:30, so around 9, we'll try to pick this back up.